It's been 4 decades of a long journey, but now the Voyager 2 spacecraft has finally bid farewell to our solar system, and it's entered the realm of the unknown.
It lay in eerie silence for 7 long months, adrift and forgotten beyond our solar system, until it vanished from all contact after decades of streaming data from the edge of everything. NASA feared the worst. Had their 1977 spacecraft finally gone dark forever? Then out of the void came a signal, not just a faint blink, but a full transmission, a message that has left scientists baffled. Was it a system glitch or proof that Voyager 2 encountered something we always suspected might be out there? Keep watching to the very end as we decode this cosmic mystery. Edge of the solar system. Imagine a lone spacecraft, launched when folks were still wrangling with floppy disks, now sending signals from the edge of the unknown. The story begins on August 20th, 1977, when engineers at JPL, that's the Jet Propulsion Laboratory, rolled Voyager 2 out of its clean room, strapped it atop a Titan IIIe rocket, and held their breath. The goal was as wild as it sounds: send a probe beyond every planet out to Neptune and Uranus, using only the slimmest sliver of sunlight and 69 kilobytes of onboard memory. That's less than the memory of a modern digital watch. From the start, Voyager 2 was bristling with gadgets built for survival. 16 hydrazine thrusters stood ready to nudge the craft back on course whenever a slight wobble threatened to spin its giant dish away from Earth. Gyroscopes and a star tracker, which locked onto Canopus, a bright star, as well as the sun, formed part of the Attitude and Articulation Control Subsystem, AACS for short. Redundant units waited in the wings like spare tires on a long road trip, plus 8 backup thrusters in case a main thruster sputtered out. Every piece of gear could be toggled to its twin if something failed. Power came not from solar panels because they'd be useless so far from the sun, but from 3 radioisotope thermoelectric generators, RTGs. Those units quietly burned plutonium, producing heat that slipped into electricity to run instruments for decades. By design, they were meant to last until around 2025, which means today Voyager 2 is still ticking off milestones long after designers hoped it might go silent. Beyond basic survival gear, Voyager 2 carried 11 scientific instruments. There was a magnetometer to track Jupiter's mighty magnetic field, a cosmic ray detector to measure high-energy particles, and an ultraviolet spectrometer to gauge atmospheric makeup. The imaging system, 2 cameras on a pivoting boom, captured breathtaking shots, but they had to squeeze those photos into that tiny 69 kilobytes of memory before sending them, bit by bit, across billions of miles at a painstaking 115 kilobits per second. At that rate, downloading a single photograph took hours. In April, a near-fatal hiccup almost silenced Voyager 2. The main radio receiver quit, and though the backup kicked in, a tiny capacitor in it soon failed too. Suddenly, NASA had to whisper to the probe on an ultra-precise frequency that could drift with temperature changes, Earth's rotation, and even solar activity. Engineers pored over their calculators, no autopilot here, figuring out the exact frequency for every single message sent. It was a nail-biter, but that crisis underscored why Voyager 2 carried twins of the most critical parts, and just how quick on their feet JPL's team could be. Fast forward to July 1979, Voyager 2 swooped past Jupiter, marking its closest dance with the giant planet. Voyager 1 had beaten it there in January, coming in tighter for jaw-dropping, high-def views. But Voyager 2's slightly wider swing was no second fiddle. That path let it linger longer near the moons, rings, and magnetic field, collecting data that Voyager 1 simply couldn't grab. By comparing data from both probes, scientists could, for the first time, confirm the volcanic eruptions on Io that Voyager 1 had spotted. Imagine it, the first active volcano ever seen beyond Earth. Lava fountains hundreds of kilometers high, sulfur plumes glowing against the black sky. Voyager 2's instruments, though not as close, took fresh measurements of the eruption's temperature and speed, painting a fuller picture of Io's wild tidal force storms. Beyond the volcanic fireworks, Voyager 2's cameras and sensors traced subtle shifts in Jupiter's rings and mapped more of its moon's rugged landscapes. Data packets dribbled in, each one a small victory after the April radio scare. In the end, Voyager 2's Jovian flyby wasn't just a footnote to its siblings' triumph, it was the yin to Voyager 1's yang, a perfect pairing that turned a daring mission into a two-act legend of exploration. 17,000 frames. When Voyager 2 reached Jupiter on July 9, 1979, the Deep Space Network dishes on Earth blinked with anticipation. At 22:29 UT, the craft made its closest approach, about 400,785 miles from the storm-racked clouds. Scientists hunched over consoles as pixel-by-pixel downlinks revealed new rings and moons. Although Voyager 1 had already supplied snapshots, Voyager 2 added fresh surprises. The ring system turned out to be more complex, and the newly discovered moons, Métis and Adrastea, twirled closer than anyone guessed. By the close of its Jupiter run, Voyager 2 had sent home roughly 17,000 new pictures. It tracked shifts in the Great Red Spot, a gigantic storm older than recorded history, watching its shape warp and its color drift toward a paler orange. Back when Pioneer 10 and 11 did flybys, the spot hardly budged. But here was proof that Jupiter's atmosphere was more alive, more changeable than anyone assumed. Behind every image and data packet were teams of scientists and engineers. They raced to write new software routines, stored in that tiny memory, to swap camera filters, adjust exposure times, and reroute data when solar flares threatened to corrupt bits. Missed the right command by a few minutes, and you lost an hour-long volcano watch forever. Radio signals took almost an hour to make the round trip, so every command sequence had to be perfect on the first try. Voyager 2 wasn't just sending back images, it was reshaping our understanding of the universe. After the spectacular Saturn flyby in 1981, the probe drifted in quiet darkness for 4.5 years, coasting from Saturn toward Uranus. That cruise might look idle on paper, but behind the scenes, program scientists and engineers were busy. They tweaked Voyager 2's software, squeezing more efficiency out of every line of code. They upgraded NASA's Deep Space Network, DSN, stations on Earth, returning antennas and amplifiers to catch fainter signals. Together, those tweaks let Voyager 2 snap and send back as many as 200 images each day, even under Uranus's dim sunlight. When January 24, 1986 rolled around, Voyager 2 hit its Uranus target at just 81,600 kilometers above the cloud tops, close enough to peer into the planet's blue-green haze. Cameras recorded the planet's tilted axis, 98 degrees off its orbital plane, showing how its poles spent decades in daylight or darkness. Voyager 2 also revealed a surprisingly complex system of 9 faint rings, barely visible from Earth, but made clear by backlit sunlight. On top of that, its infrared spectrometer found methane clouds riding high and fast winds, clocked at up to 900 kilometers per hour, that raced around the planet's waste. Through all this, Voyager 2 stayed healthy. The scan platform glitch that had threatened earlier encounters never reoccurred, and the RTGs were still putting out enough juice to keep instruments alive. After the Uranus flyby, the spacecraft turned its high-gain antenna back toward Earth and barreled onward, aiming for Neptune in August 1989. By the time Voyager 2 reached Neptune, it was visiting the most distant world known to humanity. Pluto was still classed as a planet then, but it lay inside Neptune's orbit. Discovered on September 23, 1846, by Johann Galle based on Urbain Le Verrier's calculations, Neptune had drawn astronomers for nearly a century and a half. Neptune proved to be more alive than expected. Its diameter of 49,240 kilometers, just a shade smaller than Uranus, hit a world of turbulence. Then there were the moons. Out at Uranus, Voyager 2 found 10 new satellites, but Neptune's neighborhood was stranger. Only 2 moons had been spotted before. Triton, found 17 days after Neptune's discovery in 1849 by William Lassell, and Nereid, discovered in 1949 by Gerard Kuiper. Where Uranus's moons marched neatly around the equator, Triton orbits backward, retrograde, at an inclination of 157 degrees, and Nereid loops on a stretched path that takes almost a year to complete. Voyager 2's photos showed Triton's icy surface scarred by cantaloupe terrain and geyser-like plumes of nitrogen gas. Proof that even far from the Sun, worlds could be geologically alive. Comparing Neptune data with Voyager 2's earlier Uranus finds lets scientists test theories of planet formation and moon capture. Triton's odd orbit backed up the idea that it was once a dwarf planet wandering the Kuiper Belt, snatched by Neptune's gravity and flung into a retrograde dance, probably wrecking a busier family of moons in the process. Nereid's stretched orbit may be the odd survivor of that cosmic shuffle. Once the Neptune data stream finally faded, Voyager 2 didn't stop. It plunged on toward the fringes of the sun's influence. In August 2018, at around 121 astronomical units from the sun, it crossed the heliopause, the boundary where the solar wind gives way to interstellar space. Instead of a hard wall, Voyager 2 found a porous, shifting membrane, alive with turbulent magnetic fields and bursts of cosmic rays leaking in. Its instruments recorded density spikes in plasma, confirming that the solar bubble isn't empty, but a living frontier. The silence breaks. For decades, Voyager 2's faint beeps were like an old friend's distant greeting, each one a tiny triumph, hopping across billions of kilometers. Then in March 2020, the Deep Space Network's Goldstone 70-meter dish went quiet. At first, everyone thought it was routine maintenance, but weeks passed with no chatter. Engineers flipped switches, reloaded command scripts, even swapped antennas, yet still nothing. Had Voyager 2 finally slipped beyond reach? Had the endless dark at last claimed it? In October 2020, hope flared. A simple, "Are you there?" command blasted toward Voyager 2, and to everyone's astonishment, it answered. Not just with a heartbeat-style ping, but with a full data dump. Telemetry streamed back, showing the probe had re-aimed itself, updated navigation tables, and recalibrated its gyros, all without a hitch. After nearly half a year of silence, it stepped right back into the dance, as if the silence had never happened. But then came the real surprise. Hidden in the data were readings from instruments thought long dead. The plasma science experiment, quiet since Uranus, now clattering to life. The photopolarimeter, silent since Saturn, now flickering on. Engineers stared at screens as subsystems once parked in safe mode began reporting voltages and temperatures, alive after decades of dormancy. It was as if Voyager 2 had been nudged awake, or someone had kicked its circuits into action. Even more puzzling were the signal patterns. Voyager 2 usually talks on well-known S and X band frequencies, but now its packets rode on strange sidebands. Echo pulses bouncing back milliseconds after the main signal. Binary sequences appeared that didn't match any log of commands NASA kept. Independent researchers picked apart the code fragments embedded in the downlink and found something uncanny. Routines from Voyager's original 1977 flight software, but rearranged in loops that reference themselves. Recursive calls folded like digital origami. NASA's public line blamed a radiation-induced glitch. A high-energy particle had tripped a memory cell, looping commands in a way no one foresaw. But inside documents quietly leaked by former contractors, one phrase kept popping up: unknown interaction detected. That three-word note, scrawled in the margins of engineering logs, hinted at something no one wanted to admit, that Voyager 2 might have bumped into an external agent in interstellar space. Think about it. Beyond the heliopause lies a sea of cosmic rays, magnetic waves, and plasma currents. Voyager 2 crossed that boundary in 2018, discovering the solar bubble's edge is more like a bruise on the galaxy, a shifting, porous membrane.
The Voyager 2 spacecraft has crossed a boundary that marks the start of interstellar space.
Could a knot of magnetic turbulence have reached in and toyed with Voyager's electronics? Or was it something even stranger? An organized structure in space that recognized Voyager as a probe, then mirrored its own code back at it? Either way, the result was the same. Voyager 2's systems, decades old, came alive in ways no one predicted. Engineers raced to decode the recursive loops, wary that the probe might lock up again. They patched flight software from Earth, sending new routines to break out of the loops. Night shifts at JPL turned into a vigil, tracking every blip, every echo. And through it all, Voyager 2, alone in the dark, kept talking. What does it mean? If this were just a cosmic hiccup, it still reveals how wild interstellar space really is. It's not an empty void, but a living realm of forces we barely understand. But if someone or something out there nudged Voyager into this odd dance, then the probe has become more than a messenger. It's a meeting place, a point of contact between human craft and whatever lurks beyond. For now, NASA stays quiet on the unknown interaction line. They're updating manuals, rerunning tests, and debating how to classify the data. Publicly, it's all routine anomaly work. Privately, some engineers whisper about the day Voyager 2 might show up in our sky, not as a spaceship, but as a beacon, reflecting back our own code in ways we never imagined. Powering down Voyager 2. Voyager 2's power comes from 3 radioisotope thermoelectric generators, RTGs for short, that quietly turn heat from decaying plutonium-238 into electricity. Between the two Voyagers, Those RTGs lose about 4 watts of power each year. 4 watts isn't much. Think of a tiny nightlight. But in space, every watt counts. Back in the 1980s, after both probes finished visiting Jupiter and Saturn, NASA started turning off instruments one by one. That gave each Voyager a chance to keep working far longer than the original plan. In October 2024, engineers powered down Voyager 2's plasma science experiment. That instrument had been measuring how charged particles, plasma, flow past the spacecraft as it drifts beyond the sun's bubble, the heliosphere. Over the years, Voyager 2's spin and tilt meant the plasma detector only caught snippets of data. Shutting it off freed up just enough juice to keep other instruments alive for another full year. Voyager 1 faced similar cutbacks. Its plasma instrument broke in 1980 and was limping along until 2007, when NASA finally switched it off to save power. More recently, back in late February 2025, they turned off Voyager 1's cosmic ray subsystem. Those 3 telescopes had been key to proving Voyager 1 had crossed into interstellar space by measuring high-energy particles flowing in from outside our solar bubble. Now Voyager 2 is set to retire another instrument, the low-energy charged particle detector, which tracks ions, electrons, and cosmic rays from both the sun and deep space. With that off, engineers expect to stretch the remaining RTG power to squeeze out another year of science, the last data from the fringe of our solar system before more tools go dark. Every shutdown is a tough call. The Voyagers have far outlived their original mission, says Patrick Coyne, Voyager program scientist. Every extra bit of data since then has been a bonus, vital for studying the space around us, and proof of the superb engineering that went into these spacecraft nearly 50 years ago. It's worth noting that no other human-made object has ever reached interstellar space. Once Voyager 2's instruments go silent, we'll lose our only ears out there. Inside JPL's control room, power budget meetings have become regular rituals. Engineers crunch the RTG decay rate. Plutonium-238's half-life is 87 years, so the generators lose about 0.8% of their power every year. They weigh each instrument's scientific value against its juice draw. The magnetometer, for example, uses only a fraction of a watt, but reveals how interstellar magnetic fields tug and twist. The ultraviolet spectrometer, a half-watt consumer, measures distant hydrogen clouds that light up when struck by solar radiation. Those instruments are safe for now. Meanwhile, the remaining tools are being reprioritized. The magnetometer and spectrometer get daily power windows. The imaging system, cameras long silent, remains off since there's nothing left to photograph. The engineering cameras, still functional, peek at the spacecraft's own thrusters and antenna alignment, giving teams on Earth a kind of health check during rare maintenance commands. Communications, too, require power. Voyager 2's 3.7-meter high-gain antenna must stay pointed at Earth, which eats a few watts for the stabilizing thrusters. Every time NASA sends a command or Voyager sends back data, those RTGs are at the limit.
It actually happened last year, but NASA only confirmed the data on Thursday.
Early in the mission, each RTG produced about 470 watts. Now, more than 47 years later, each makes closer to 250 watts. Of that, only about 20 watts remain for science instruments. The rest goes to the radio, heaters, and essential avionics. To manage this, engineers have written new sleep modes into the flight software. When Voyager 2's instruments aren't in use, they're parked in low-power states. The flight computer itself, with its meager 69 kilobytes of memory, juggles these schedules, waking instruments only at preset times. It's the modern equivalent of shutting off lights in rooms you're not using, but in space. All of these moves come with risk. Powering down an instrument means one less way to catch new discoveries. What if an unexpected solar storm reaches Voyager 2, or a rare burst of interstellar particles? We'll only know if the detectors are on, but the reality is clear. Once those RTGs dip below the threshold needed to power critical systems, about 157 watts total, Voyager 2 will go silent forever. Still, there's a bittersweet thrill in this final stretch. For nearly half a century, Voyager 2 has been our outpost in the cosmic sea, drifting farther each day. Every last data packet it sends home reminds us how far we've come with just a handful of watts and a daring vision. Soon, NASA will celebrate one final transmission, the spacecraft's goodbye wave, before it drifts into permanent quiet. Now it's time for today's subscriber pick. Monday afternoon at the Deep Space Network, signals crackled like an SOS. Lena scanned the screen with her heart pounding. For months, Voyager 2 had ventured deeper than any human-built device, radioing tales of silent rings and icy exospheres. No log entry prepared them for this. Voyager 2 just turned back and confirms what we all feared. The message arrived as a string of data in a single chilling image, a yawning void where distant stars blinked out. All those theories about a cosmic phantom zone were suddenly real. Dr. Adebayo tapped his pen against his clipboard, voice steady even as his hands shook. They had always hoped for glory, proof of new worlds, traces of hydrogen seas. Instead, they found a darkness that swallowed starlight. Outside, the control room lights dimmed. Global radio telescopes fell silent, as if the world itself held its breath. The control room's hum felt distant under that weight. Lena felt a shiver settle in her chest. The probe's retreat suggested an unseen force, something more alive than any meteor or black hole. If Voyager 2 ran for its life, what chance do we have? What waits beyond that horizon, watching us in return? The Voyager anomaly. Voyager 2's voice is growing faint, like a friend slipping into a dream. Every week, NASA's antennas strain harder to catch its whisper, trying to pull every last byte of data from the distant probe before its signal fades forever. Behind the scenes, scientists race against time, feeding Voyager's final transmissions into supercomputers, hunting for revelations that could change how we see our place in the cosmos. In one late-night session, analysts stumbled onto a patch of telemetry that raised red flags. It arrived just before March 2020's blackout, a block of numbers that didn't fit any known pattern of interstellar plasma or magnetic fields. Rather than random noise, the data formed neat, periodic pulses, like ripples hitting a shore at precise intervals. A report noted localized pressure differences around the spacecraft that no one expected. Not the usual jostling of the heliosheath, but something pushing in, pressing against Voyager's immediate space. Theories flew fast. Maybe a hidden brown dwarf, a dim, failed star, drifted close enough to leave a gravitational wake. Or perhaps Voyager had drifted through a stable bubble, an unseen corridor of altered space where conditions held constant against the solar wind. Word of these ideas didn't make it into press releases, but inside certain labs, some with secretive government ties, simulations began to hum. And the results were eerily clear. Voyager 2 had passed through something that didn't just tweak its surroundings, it seemed to change how the probe itself behaved. Deep space missions have long worried about forward contamination. D-Day freezers of bacteria hitching rides on spacecraft, potentially seeding alien worlds. Engineers sterilized probes in surgical clean rooms, scrubbing off anything living. But Voyager 2 raised a new fear: informational contamination. Could the probe, sailing through a field of unknown energy or structure, have absorbed patterns that rewrote parts of its code? When the backup software awoke in October 2020 and began sending recursive loops, subroutines calling themselves like Hall of Mirrors code, some engineers saw intent in the glitch. Not a mere error, but the probe acting with a kind of agency. Inside JPL's mission control, a hush fell over public operations. A special team, separate from the day-to-day Voyager group, took over monitoring Voyager 2's signal. Their orders: listen, log, and don't reply, unless told otherwise. The reason? The downlink had become unpredictable. Signal strength sizzled in sudden spikes, not from power fluctuations, but in bursts that echoed solar storms that weren't happening. Pulse intervals began to mirror patterns from Voyager 1's early interstellar readings, only flipped end to start, like last night's dream replaying in reverse. Speculation ran wild. Some scientists whispered about cosmic resonance, a feedback loop between a human-made machine and an unknown structure in deep space. A force field, a gravitational eddy, or yes, an intelligence beyond our ken. Others warned that if we start answering back, we could trigger something we can't control. The leaked memo captured that tension in just 4 words: maintain position, do not respond unless instructed. Meanwhile, the public continued to see dry updates. No science data this week, but inside vaulted rooms, teams pored over every scrap of Voyager 2's last transmissions. They replayed the odd telemetry, ran it through pattern recognition algorithms built to spot everything from pulsar echoes to coded messages. Every anomaly got cross-checked against solar weather logs, galactic cosmic ray monitors, even distant supernova databases. Nothing outside Voyager 2's local bubble matched the patterns. It was as if the probe's own history was filtering back through the interstellar medium, transformed. In late April 2025, that special monitoring crew detected a shift. For the first time, Voyager 2's signal briefly tuned back to its original X-band frequency, the one used in the 1970s, before slipping again into those strange sidebands. The change lasted only seconds, but it was enough to make hearts pound. Had someone, or something, recalibrated the probe? Or was the craft itself seeking to reconnect on its own terms? NASA's official lines still blamed random bit flips from cosmic rays, but insiders know the story's more tangled. Committees debate the risk of slewing DSN dishes to chase Voyager 2's erratic signal versus conserving the last watts of power for science instruments. Each day, they weigh the chance of squeezing new insights against the danger of provoking a response they can't predict. For now, Voyager 2 keeps talking. Its pulses carry secrets of distant space, pressure waves that don't fit our models, echo patterns that hint at structured fields, and code fragments looping back on themselves. As those antipodal echoes of Voyager 1 remind us, our two probes may be tracing hidden currents in the galaxy, currents we never knew existed, from 5 years to forever. Voyager 2's journey reads like a science fiction tale come to life. Launched in 1977 with a 5-year ticket to explore Jupiter and Saturn, it wound up soaring past Uranus and Neptune, then slipped out of the sun's reach and into interstellar space. Along the way, it rewrote our cosmic playbook. First stop, Jupiter in 1979. Voyager 2 revealed new rings, discovered tiny moons, and watched Io's volcanoes erupt in towering plumes. When it sent back photos of Europa's cracked, icy shell, scientists began dreaming of hidden oceans beneath that frozen crust. Then came Saturn in 1981, where Voyager 2 found more rings than anyone guessed, and fine spokes of dust flickering in the planet's shadow. After that, the probe coasted for 5 years in quiet darkness, before swinging close to Uranus in 1986. Under dim sunlight, Voyager 2's upgraded cameras and spectrometers spotted 9 faint rings in a set of dark, tilted storms, whipping methane clouds into fast-moving bands. It mapped 10 new moons and measured winds racing at nearly 900 kilometers per hour, fast enough to lap a jet fighter dozens of times. Even now, more than 47 years after launch, Voyager 2 keeps talking, its tiny 69 kilobyte memory still streaming data at just 115 per second. Every bit it sends home, whether a magnetic field reading or a quick health check pulse, is a precious gift from the edge of the known universe. Alongside its twin, Voyager 1, Voyager 2 carries the golden record, a time capsule of sounds and images from Earth. It's a reminder that our little blue dot sent messengers into the void, hoping that whoever, or whatever, finds them someday will know where they came from. Few missions have matched Voyager 2's mix of daring and endurance. Instruments designed for 5 years kept working for decades. Engineers back on Earth rewrote software in flight, mended glitches from billions of kilometers away, and planned shutdowns of non-essential tools to squeeze out extra months and years of operation. Voyager 2 has given us unprecedented views of the outer planets and their moons. It has taught us that distant worlds can be dynamic, volcanic even, where we once expected only frozen rocks. It has been shown that space isn't empty, but alive with particles, fields, and currents we're only beginning to map. As its power wanes and its faint signal drifts towards silence, we're racing to capture every final bite. Voyager 2 has already far outlasted its creator's wildest hopes. Its story reminds us that bold ideas, in a few watts of power, can carry humanity's curiosity farther than we ever imagined, and that the universe still holds surprises waiting for those willing to listen.